Have you ever walked into a dark room and flipped a switch? In that moment, you're surrounded by darkness, unable to see what's around you. But with a simple motion, you press the switch, and suddenly, everything changes. Instantly, the room is filled with light, shadows disappear, colors return, and the space feels alive again. It's a transformation that happens in the blink of an eye, and it's something we often take for granted. It feels like magic, but it's really science in action. The light that fills your room is the result of a fascinating journey, one that starts far away and ends right above your head. That simple flick of a switch sends electricity racing through hidden wires, weaving its way through the walls and ceilings of your home to power your light bulb. These wires are like secret highways, carrying energy from one place to another. So, where does that light really come from? The story begins at massive power plants where energy is generated and sent out across miles of high-voltage power lines. Let's explore the world of electricity and discover how it all connects. When you flip the switch, you're actually opening a tiny gate in an electrical circuit, letting electricity flow at nearly the speed of light. This invisible current rushes through the wires, bringing energy to your light bulb and making it glow. This isn't just for lights, it's how your TV turns on, how your phone charges, and how your refrigerator keeps your food cold. Every device in your home depends on this same flow of electricity to work. Every time you turn something on or plug in a device, you're completing a path for electricity to travel. It's like opening a door and inviting energy inside to do its job. Electricity is a powerful force that makes our modern world possible. It lights up entire cities, powers transportation, and connects us in ways people 100 years ago could only dream of. We'll break down this magic into simple pieces: how tiny particles called electrons move, the paths they travel through wires and circuits, and how we control them with switches and buttons. By the end, you'll see that the science behind your light switch is more fascinating than any magic trick. So, get ready to uncover the secrets of electricity and discover the incredible journey that brings light into your life. Let's get started. Everything is made of atoms, tiny building blocks with a nucleus at the center, and energetic electrons whizzing around. Electrons are the real stars of our electricity story. In some materials, outer electrons aren't held tightly and can jump from atom to atom. This chain reaction of jumping electrons creates a flow, what we call electricity. Imagine a tube of marbles. Push one in, one pops out the other end. That's how electrons move in a wire. Electricity is the controlled movement of these restless electrons. We've learned to create a push to get them moving and built pathways for them to travel. From a spark to city power grids, it all starts with the humble electron. Science lets us harness this invisible dance for everything we do. Pretty cool, right? Electrons need a complete, unbroken path, a circuit to flow. Think of it as a racetrack, the power source, the device, like a bulb, and a return path. If there's a break, the race stops, no flow, no light. Let's picture a simple battery circuit. Connect wires from the battery's negative to a bulb, then back to the positive. Complete the loop, and electrons flow, lighting the bulb. Inside the bulb, electrons push through a thin filament, making it glow. This continuous flow is called electric current. Open the switch, and the flow stops. The light goes out. Every device, from flashlights to computers, relies on this closed-loop principle. Circuits are the foundation of all electrical technology. Without a complete path, nothing works. That's the secret behind every switch you flip. To understand circuits, imagine electricity as water flowing through pipes. This analogy helps us grasp the fundamental concepts of how electrical circuits work by comparing them to something more tangible and familiar. Voltage is like water pressure. It pushes electrons through the wire. Just as a high-pressure water pump forces water through pipes, a higher voltage pushes more electrons through the circuit. A higher voltage means a stronger push, just like a taller water tank creates more pressure. The greater the height of the water tank, the more forcefully the water flows out, similar to how higher voltage drives more current. Current is the flow rate, the amount of electrons passing a point per second, like water flowing through a pipe. The faster the water flows, the higher the current, indicating more electrons moving through the circuit. A thick wire, like a wide pipe, carries more current. A thin wire carries less. Just as a wider pipe allows more water to flow through, a thicker wire can carry more electrical current without overheating. Resistance is anything that makes it harder for electrons to flow, like gravel in a pipe. This obstruction slows down the flow of water, just as resistance in a wire slows down the flow of electrons. The filament in a bulb has high resistance, turning electrical energy into heat and light. When electrons struggle to pass through the filament, they release energy in the form of light and heat, illuminating the bulb. Voltage, current, and resistance work together to determine how much electricity flows. These three elements are interdependent, much like the components of a water system, ensuring the circuit functions correctly. We use resistance to control and convert electricity into useful forms. By adjusting resistance, we can manage the flow of electricity, similar to how a valve controls water flow in a pipe. This analogy helps us visualize what's happening in every circuit. By comparing electrical circuits to water systems, we can better understand the invisible forces at play. Remember, more voltage, more push, more resistance, less flow. This simple principle is key to understanding how electrical circuits operate and how we can manipulate them for various applications. That's how we power everything from tiny LEDs to giant factories. Simple, right? By mastering these basic concepts, we can harness the power of electricity to drive innovation and technology in countless ways. Not all materials let electrons flow easily. In fact, the way a material interacts with electricity depends on its atomic structure. Some materials are like open highways for electrons, while others are more like brick walls. This difference is what makes our modern world possible, allowing us to control where electricity goes and how it's used. Conductors like metals are superhighways for electricity. Electrons move freely. In these materials, the outer electrons are loosely bound and can travel from atom to atom with ease, creating a steady flow of electric current. This is why metals are used everywhere in electrical systems, from the smallest circuits to massive power grids. Copper is the most common conductor in wiring. It's affordable, flexible, and conducts electricity very efficiently, making it the go-to choice for most electrical applications in homes and industries. Gold and silver are even better conductors, allowing electrons to move with even less resistance. However, their high cost means they're reserved for specialized uses, like high-end electronics or critical connections where performance is key. Water with minerals is also a conductor, why electricity and water are a dangerous mix. Pure water doesn't conduct well, but the minerals and impurities in everyday water create pathways for electricity, increasing the risk of shock or short circuits. Insulators like plastic and rubber are roadblocks. Electrons can't move through them easily. These materials have tightly bound electrons that resist the flow of electricity, making them perfect for keeping us safe from accidental shocks. That's why wires are coated in plastic. It keeps electricity inside and protects you. The insulation acts as a barrier, preventing the current from escaping and making sure it only travels where it's supposed to. Conductors and insulators work together. Conductors carry current, insulators keep it safe. This partnership is at the heart of every electrical device, from simple lamps to complex computers. The metal prongs on a plug are conductors. They connect your device to the power source, allowing electricity to flow in. The plastic casing is an insulator, shielding your hands from the live current and making the plug safe to handle. This teamwork makes electricity both useful and safe. Without it, even the simplest task, like plugging in a lamp, could be dangerous. Understanding which materials conduct or block electricity is key to safety. It helps us design safer homes, workplaces, and devices, and teaches us how to avoid electrical hazards in everyday life. Every cord, plug, and device uses this principle. The right combination of conductors and insulators ensures that electricity goes exactly where we want it, powering our lives without putting us at risk. It's how we control and direct the power we use every day, from lighting our rooms to charging our phones and running entire cities. That's the partnership behind every safe electrical device, a careful balance of superhighways and roadblocks, working together to bring the power of electricity safely into our hands. Electricity in your home starts its journey at a power plant. Power plants spin turbines using steam, water, or nuclear reactions to generate energy. The spinning turbine turns a generator, a magnet spinning inside coils of copper wire. This motion pushes electrons, creating electric current. Electricity travels long distances on high-voltage transmission lines, those tall towers you see. When it reaches your neighborhood, transformers lower the voltage to safe levels. The electricity enters your home through a panel, then waits in your walls for you to flip a switch. From power plant to your outlet, it's a carefully managed journey. Every step ensures electricity arrives safely and efficiently. That's how the power gets to your fingertips. AC/DC isn't just a rock band, it's two types of electric current, alternating current AC and direct current DC. DC flows in one direction like water in a river, batteries power devices with DC, AC switches direction rapidly like waves. This is what comes from your wall outlets. Power plants generate AC because it's easy to change its voltage for long-distance travel. AC can be stepped up for transmission, and stepped down for safe use at home. That's why AC powers our grid. Many devices like phone chargers convert AC from the wall into DC for batteries. You use both types every day, AC for your home, DC for your gadgets. Understanding the difference helps explain how our devices work. The world runs on both, each with its own strengths. AC for distance, DC for precision. That's the current story. Electricity is powerful and dangerous if not respected. The human body conducts electricity, so safety is crucial. Never mix electricity and water. Wet hands lower your resistance and increase shock risk. GFCI outlets in kitchens and bathrooms shut off power instantly if there's a problem. The third prong on plugs, the ground wire, gives stray current a safe path to the earth. Damaged cords or overloaded circuits are hazards. Always check and fix them. Never stick anything but a plug into an outlet. Follow these rules to enjoy electricity safely. Respect the power and stay safe. The future of electricity is cleaner and smarter. Solar panels turn sunlight into DC electricity. No moving parts, just pure energy. Wind turbines use the wind to spin generators, producing AC electricity without emissions. Renewables are making our power grid more sustainable and resilient. Electric vehicles use big batteries to power motors, no gas, no tailpipe emissions. Smart grids use digital tech to manage electricity efficiently, reroute power, and save money. The way we generate, use, and store electricity is changing fast. Cleaner energy and smarter systems are shaping our future. The science of electricity keeps evolving. Stay curious, there's so much more to discover.